Chris Davis has been working in the facade business development team at HP Fuller since 2019 in the building products sector, developing liquid optically clear adhesive range of products. That sounds a mouthful. That sounds great. His role requires close liaison with process partners in the business, product development, and working with building designers, engineers, and academic institutions. So please, a warm welcome for Chris.
Yank, thank you so much. And it's great to be in Finland, isn't it? It's great to be back here in GPD, and thanks to the GPD team for putting on what's been an amazing conference so far. And I've no doubt that tonight we'll have an incredible farewell party, and if Olma's retirement party was anything to go by, it'll be memorable, that's for sure. I'm Chris Davis. As Yank said, I work within the business development team at HP Fuller. And for those of you who don't know HP Fuller, we're the leading supplier of adhesive and sealant solutions for facade and many other applications. And if you don't know us, that's because we're a well-kept secret. Hope that's not the case later. So sustainable glass through intelligent adhesive and sealant solutions. That sounds so dull, doesn't it? My goodness. But I'm hoping that by the time we finish the session, that you'll feel a little bit of the passion that we feel for what we do. So as building engineers, as designers, as component developers, as sealant and adhesive solutions providers, we all have this burgeoning, this incredible duty of care to the future generations. And many of us have got children, we know that story, to thoroughly understand the carbon consequence of what we do. And if anything has come through this conference as a theme, through the keynotes, through the participants' presentations, it is exactly that, and it's an incredibly important role that we play. So through principles like the carbon payback principle, through the building performance gap principle, we're guided to understand how we balance embodied carbon with operational carbon. These are all familiar terms, and also how we interrogate the metrics and the data that give us real-time values expected against real values for the performances that we expect. And there's no question that if we're able to deliver insulating glass, high-performance insulating glass that has much, much longer, and I use the word effective, and I use it a lot, effective service lives, then we will make a considerable contribution and benefit sustainable architecture. And Rebecca's work, Rebecca Hartwell, demonstrates that in her work, where she shows that if we can double the effective service life of an insulated glass unit, that we will halve its embodied carbon. That sounds pretty straightforward, doesn't it? It makes perfect sense. And in the glass development world, we've been hyper busy, we've been hyper effective and met those challenges head on to improve performances from single glazing at north of 5 watts per kilowatt squared, meter squared, to sub 1, where we're using triple glazing with multi-coatings, multi-gas filled cavities, very, very high performance, and demonstrated that we can deliver carbon savings and we can deliver cost savings, and we can even improve cold bridging performances. So we've done an incredible job, but that's not the whole story. And this is part of the challenge, that in making those improvements, developing that performance, we're increasing the embodied carbon consequence. Every time we add a coating, every time we add another leaf of glass, a process, transport, we're adding embodied carbon. So the consequence of that is, how do we balance that by utilizing those high performances for longer to affect the operational carbon consequence of the buildings that you're all designing? Our work as insulated glass sealant suppliers gives us, over decades, gives us an understanding of the hierarchy of insulation efficiency for insulating glass. And there's no question about it that the prime driver is low emissivity glass coatings. We all know that, whether they're pyrolytic or sputter coatings. But they only work really effectively, or generally really effectively, in a really gas-tight environment. That's where their optimum performance is key. And then we've developed warm edge technology. So to a lesser extent, that's also contributing to that hierarchy. And they're all important developments. But here's the challenge, and don't shoot the messenger, but actually that cavity performance is not always stable. In fact, very rarely stable. And the deterioration in the cavity performance is going to naturally impact on the U value. So the work that we do and some of the data that we have demonstrates that. So the buildings that you design and the metrics that you use in your modeling have a deviation. And that's important to consider. And you're forever designing buildings that are much, much more efficient. The metrics are more finite. So this understanding is key. And we haven't really factored in how that deterioration in the cavity affects metallized coatings. That work's going on, and it's really important to understand how that may impact in medium and long term. But the good news in amongst all these challenges is we're part of the way there, a long way there towards a solution. So our development of TPS, and thanks to the guys at Glaston, because they kind of a great warm-up for this. So our work with TPS demonstrated that you can have gas-tight, long-term gas-tight, durable insulated glass assemblies. And this data here was taken from our normal internal test data, where we test our own sealants with a multitude of different spacer systems. So there's nowhere to hide with this. But the CodySpace 4SG product at the bottom, which is our reactive warm-edge thermoplastic material, demonstrated really quickly that actually we could run it through 10 cycles and it was unbreakable. In fact, R&D was so excited, we'd never seen them so excited. So what is it? It replaces, it's an integrated system. So it replaces a conventional hollow bar system with separate primary seal. It has an integrated desiccant matrix, and it's warm edge. So when we talk about reactive, this is a chemical bonding behavior that improves the service life and durability. So what is reactive behavior? It's a hydrolysis condensation-based reaction from the polymer into the substrates and also into the secondary seal. So I'm going to add one more boundary layer to the guys at Glaston. I'm going to say there's 5. And that's important in developing an incredibly strong adhesive bond to all those interfaces. And by doing that, you're de-risking. So we talked about, the guys at Glaston talked about boundary layers, and that's absolutely true. So with an integrated system like TPS, you reduce the risk, you reduce the number of interfaces, you reduce the opportunity for dislocation. And that dislocation in both shear and in pressure. So the side benefits to this, as we discovered, are that we get extended service temperatures up to 90 degrees. So an improvement on a conventional system in our experience. And that actually this dislocation of the spacer through our testing and modeling, my technical colleagues would say it's impossible. I'm always a little bit more reserved being from UK. So I'd say it's almost impossible. Never say never. And our internal testing through climatic cycle testing and through long-term high temperature testing, both at humidity or humidified conditions, demonstrated that gas loss over 5 cycles was less than 4%. And that's pretty significant. My question is, and we'll come on to that in a second, is what does 5 cycles actually mean? So you may know better than we, but it's a significant improvement on where we've been previously. So as climates change, and so many of the presentations have detailed how that happens and the consequence of that, how your design creativity pushes the boundaries of insulated glass, all deliver a whole set of new challenges that are very current. Different load conditions, different mechanical, different pressure conditions, different cycling. So there is a question about how we view those metrics, how we look at the building performance gap. Are the current metrics that we have in terms of empirical data and testing, do we think they're still relevant? Do we need to refresh those? Do we need to review them? Maybe improve them? Do we need to look for higher performance for longer? There's work going on in terms of field assessment. So trying to balance some of that test data that we have, that great empirical data based on test units that are generally 500 by 350 millimeters, trying to balance that with real-time data from what goes on in the field. And we're already on that bus. So we have a project in China, a hospital, that was built 2010, 2011, completed 2011. And we pay a regular annual homage back to the building, and with Spotlight equipment, we carry out gas concentration testing. So the good news for us is actually our field testing tells us that we're in the right ballpark. On an average, that our gas concentration, even after 13 years of service, is still around about 95% with CODISpace 4SG. So that reactive system is demonstrating in the field that it's worked. And there is a kind of health warning with this, because, I mean, the ones of you who didn't spend too long at the conference dinner will notice that the values are going up. So there's some deviation there. And I'm sure that Spotlight have some equipment that is probably more accurate than the equipment that we currently have there. But it's in the right ballpark. Additionally, we know that through testing that gas type performance is really, really good. But what's really important for us, and to support that creative design and continue that journey without restricting it, is to understand how mechanical loading, climatic loading will affect the performance of those insulated glass units in service before they get to service. And a really great example of this is Chadstone Shopping Mall in Melbourne. So really onerous climatic conditions, as you can imagine. Massive roof, 2,000 plus square meters of glass. I don't think any of them are the same. They're all cold torsion bent, so they're under a static mechanical load constantly. So in order to have a really comfortable feeling before that building gets built and before that facade gets installed, it's really important to understand how the material works. So at Cumberland HB Fuller, within our DNA is material law. So for almost all our materials, we have material laws. We can't help ourselves. Developed from DMTA testing through mathematical modeling, then into FEA. And in this case, the material has a plastic behavior, which is non-linear, and it's actually quite complex. So we're able to model that with utilizing pressure, torsion, and shear data. And then convert that into FA modeling as validation. And that FEA modeling is available for engineers to then overlay that into their specific building design. These models are from Chadstone Mall, and during the design process there was some comparison, some understanding needed of how that roof would behave as temperatures changed, as coefficients of temperatures affected the material, and we had a question about that, which is a really valid question earlier on. And what's really clear from this model is strain dissipation, and how an integrated material like CODISpace 4SG is able to dissipate strain from those primary boundary layers. So on the right we have a conventional hollow bar system with that primary seal, which sometimes can be a millimeter or less. I mean, it's incredibly effective. It's a polyisobutyl material, the same as CODISpace 4SG. It's based on exactly the same material. So it's very high performing. But there's not a great deal of body of material to cope with that potential dislocation from mechanical shear. So you can see the concentration of strain at that interface with the glass and the primary seal. On the left, under the same load conditions, is the respective strain dissipation for Codispace 4SG. And you can see how the pale blue area shows the strain dissipating through that much greater mass, that greater body of polyisobutyl. And I think probably for me the impressive fact with this modeling is that the mechanical model for 4SG, or the FEA model for 4SG, is in fact amplified 9 times, so you can see that strain dissipation. So in practice, it's a lot lower. So that's very much about de-risking under mechanical conditions, under owner's mechanical conditions, de-risking the potential for dislocation and under high temperature. So our DMTA is obviously taken under varying temperature conditions. So hopefully that gives you some comfort that those really unusual shapes that you need to design and create to satisfy that client who's got that kind of need for a signature building can be achieved, and at the same time you're not impacting on that embodied carbon consequence of using an insulated glass unit. You're not putting undergraded duress. But it doesn't really end there. So part of what we do and part of the passion that we have is about extending that understanding into other applications and contributing to holistic, sustainable strategies. We were really, really pleased and delighted to be involved with this particular project in Seoul. It was a flagship project. It achieved a gold LEED award for combining a series of sustainable solutions, including geothermal pumps for heating, ice packs for cooling, and of course the ubiquitous BIPV and PV for energy generation. But it wasn't just a kind of tick in the box. This design was all about genuinely contributing to a sustainable strategy. The cornerstone of that building is the use of reactive thermoplastic spacer system, Codispace 4SG, funnily enough, in order to demonstrate that those insulated glass units don't need replacing in short order, that actually the longevity of that building, the performance of that cladding fabric is sustainable at an effective level. And it's not just extended as a high-performance insulated glass. That technology also encapsulates electrochromic dynamic solar control. And we know from our work in that field in new energy and that organic materials require really high-performance dry air environments to work effectively. So we're contributing on 2 levels there, alongside the passive solar control that the fins provide across the building. And the result of that is a combined collective performance that delivers almost 10% of that building's energy, the energy requirement to run the building, which is significant, so that's taking strain off the infrastructure. But it's also demonstrating that the importance of a dry air barrier and the key to longevity for that building. And we've all talked, and there's been many talks and many references to how we need to reuse material, we need to reuse buildings. We don't want to be ripping them apart and replacing them. We want to have confidence that the components can be reused and are still effective. And that's a fine example. So our commitment to using the technology, the expertise, the experience that we've developed over many, many years to promote and enable sustainable architecture, I think is quite clearly within our DNA. And that's not just about energy efficiency and effective long-term high performance for insulated glass with products like reactive 4SG, but it's also about transferring and utilizing our experience in the renewable energy sector, where we know dry air barriers are so important, and utilizing similar technologies, utilizing similar experience, being able to encapsulate thin film PV, organic coatings, and do that successfully so that they are long-term solutions. And also, in the same way, using our special interlayers to encapsulate and to embed functions in glass that make glass more effective. And I've had several conversations throughout the conference about the risk that glass is at, and we need to justify the use of glass to sustain its use as a building cladding material. And we do that by delivering function, sustainability, and longevity, and in some way being able to demonstrate disassembly. So let's not forget disassembly and the importance of that. It's my last slide, finally. So it's a sobering thought that just in the UK alone, 1.5% of carbon emissions are generated by facade construction. Just the facade bit, not knocking the building down and putting the concrete up. So, I mean, that's significant. So whatever we do to chip away at that and demonstrate that facades are sustainable vehicles of cladding for cladding buildings is hugely important. So the questions, we've probably asked more questions than we've answered, and but our questions to you, particularly in the design community, is what do you consider to be an effective service life? Is the effective point of failure dew point failure? I don't know. Is that, or are we trying to move it back a little bit to understand where the U value might be and how that impacts 2,000 square meters of roof glazing? Do we need to have a better understanding of that building performance gap, so where we draw closer together what the expectation, the real-time values are? Do we work together in terms of industrial partners and design and institutes to bring that together really quickly? And that's the other message, is we don't have a lot of time to do this, so we have to work closely together. But I think what's clear is that if we can increase the effective service life of not just insulating glass, I mean, that's our bit, that's what we do, but of all components, that effectively we're making them more effective in terms of utilizing operational carbon to reduce their embodied carbon impact. So hopefully you feel a little more enthused and a little more comfortable that we're working hard to deliver solutions that make your jobs a little easier and a little more ethical. Thank you very much.